This video we are going to look at organic chemistry with the main focus on a recap of mechanisms in year 12. Okay, let me give you a quick summary of this. Alkanes, free radical substitution. Okay, now remember this is a recap because you've already covered these topics in class. Alkenes, electrophilic addition. Halogenos, so halogeno, alkanes, nucleophilic substitution. Nucleophilic substitution. Okay, excuse the spelling please. Then we have two elimination. Alcohols, also known as dehydration, and halogenos. I'll just call them halos. Right, let's go into detail now of each one. So I'm going to look at each example and why we have that particular mechanism. Start with alkanes. Alkanes is free radical substitution. Now, remember what substitution means. In this case, substitution is where a hydrogen of the alkanes will be replaced by a radical, halogen radical. So there's the swap. Okay, right. There are three steps here. Number 1, initiation, where the halogen undergoes a breakage, or the covalent bond in the halogen breaks into two radicals. Remember what a radical is: an unpaired species, a species with an unpaired electron. There, that's why we put a dot on there. How did this happen? Well, chlorine, focus on this. In the chlorine we have the following. There's your covalent bond in chlorine. When this chlorine breaks, the breakage is known as homolytic fission. So we call this breakage homolytic fission. So when the covalent bond breaks, each chlorine takes a electron with it. The next step is propagation. There are minimum of 2 steps here. Let's use a different alkane. Yeah, let's use C2H6. Now please note now, the carbon-hydrogen bond will break to leave with C2H5 plus HCl. The dot can be anywhere, but preferably I'd like it on the carbon. Step 2 of propagation is where the radical formed in step 1 now, that's your C2H5, reacts with chlorine now, and it forms C2H5Cl plus Cl dot, and the reaction can continue now. But we've made chloroethane here. That's the important part here. Then you've got termination step, and termination step is coming together of radicals. Ending. You could have 2 C2H5 and C2H5 coming together. You can complete the rest yourself. You can have C2H5 and Cl dot, and you can complete the rest. So there's a very quick overview of free radical substitution in alkanes. Now I'm going to look at alkenes. Alkenes undergo electrophilic addition. The reason is alkenes have a electron-rich double bond. This double bond here is electron-rich. Think of it as a negatively charged area. It will now attract an electrophile. Electrophile is E+. Let's treat electrophile E+. An electrophile is an electron deficient species, which means that it is something that needs an electron or a pair of electrons. The proper definition of electrophile is it is an electron pair acceptor to form a covalent bond. Okay, let's look at the mechanism now. We're going to do this mechanism with HBr, and I'm going to use propene. So there's propene and HBr. Okay, let's do some color coding here. Let's draw HBr in red. Okay, so here's HBr. Bromine is more electronegative than hydrogen, so it will draw a pair of electrons towards itself. There. Leaving the hydrogen electron deficient, please note an arrow will come from the double bond in carbon towards the hydrogen. Make sure this is a curly arrow, because a curly arrow shows a movement of a pair of electrons. That forms the following now. Now, the first thing is, because it's an addition reaction, the carbons around the double bond are not losing anything. Now, where are we going to attach H and Br? Where will HBr attach now? I'm going to attach my hydrogen here. Put positive there on the carbon, and this form of breakage, the way HBr broke, we call this heterolytic fission, because the Br, being more electronegative, has taken the pair of electrons in the covalent bond. A arrow will now come from the lone pair towards the delta plus carbon, and there's your molecule. There's your product now, 2-bromopropane. Now, just a quick note, and I'm not going to go into too much detail here, I'm just going to mention this. You do need to know about the stability of carbocations, and you can have a read of yourself as to why 2-bromopropane in this reaction is the major product as opposed to 1-bromo. But anyway, I'm going to leave that because my focus mainly is to tell you how to do a mechanism properly. Next one is going to be electrophilic substitution reactions of, next one is nucleophilic substitution of halogenoalkanes. Substitution of halogenoalkanes. Halogenoalkanes have a halogen attached. Because of the halogen, this makes the C-halogen bond really polar. Bromine is more electronegative, and because of this polarity, the bromine attracts a pair of electrons towards itself, making it so attracted a pair of electrons towards itself. That means that the carbon now has become electron deficient. So that has made this carbon electron deficient. There. So it's electron deficient. That means this carbon will now be attacked by a nucleophile. And I'm going to use cyanide as my nucleophile. With cyanide, please note the minus is on the carbon with the lone pair on the carbon, and an arrow goes to the carbon like this. So again, see, it's the nucleophile which is known as an electron pair donor as opposed to an electrophile, and now you have the following product formed. Extremely important reaction, and it's increased the carbon chain length by 1. Let's look at, so I've only given you one example. Remember, with halogenos you need to know the reaction with, say, sodium hydroxide and with ammonia also. Right, now the last two examples, elimination reactions. Let's look at halogenos first. Right, this one I think is the easiest one. So here's my halogeno, 2-chloropropane, and the conditions here are very important. We're going to use ethanol as a solvent, so it's ethanolic conditions. Here hydroxide is going to act as a base now, and a base is a proton acceptor. So let me do the arrows in red for you. The product is an alkene, so the CCl bond breaks. There's one arrow. The hydroxide will take the hydrogen on the adjacent carbon, and the CH bond that breaks comes back in to form a double bond, and there's your product. So it is a electrophilic, it's an elimination reaction, and other products could be water and chloride. Okay, the elimination of alcohols is slightly different. In alcohols, your catalyst is sulfuric acid, and we're going to represent H plus as sulfuric acid. You do need to know how sulfuric acid breaks, so just for a quick recap, always write sulfuric acid like this: delta plus hydrogen, delta minus oxygen, and it breaks to form the hydrogen bond. Anyway, let's do the mechanism because that's more important. Again, I'm going to use propan-2-ol, and I'll draw it like that. The lone pair on the oxygen in the OH will attract the H plus. Step 1. Step 2 is the following. The OH2 becomes like that with the positive on the oxygen, and all that's going to happen. And now let me use red arrows. The bond between carbon and oxygen breaks, and this bond here also breaks, and this hydrogen here is taken by this part of sulfuric acid. Because it's a catalyst, it reforms, and your product now is going to be propene plus water. That's why we also call this reaction dehydration. There are the mechanisms. There are some mechanisms you need to do in more detail, but that's, I think, a nice summary in about 15 minutes of all the mechanisms in organic chemistry. So there's all your mechanisms done.